Last time we started discussing the batch distillation when we have stages on top of the still pot. So we said we derived the equation for the simple batch distillation, and we said this one and the composition and the distillate instantaneous composition of the distillate and an instantaneous composition of the residual, both are at equilibrium. Okay. Today we will see if we have stages like these ones here. And now I would like just to find the relationship between these two here. So now here they are not at equilibrium, but they are related by the rectification section, and the relationship between the XD or instantaneous XD and instantaneous XW, the mole fraction of the more volatile component in the residual and the mole composition or the mole fraction of the more volatile component in the distillate are related by or are affected, the relationship is affected by the number of stages. Okay, will depend on the number of staging and their flux ratio. So this relationship is function is dependent on both flux and number of stages. Number of stages above, of course, the still pot here. So we said this is our equation, in fact, and this is what we're trying to solve. But as I said here now, the x and y are not related by equilibrium anymore. They are related by the operating line of the rectification section, which is this one here. And as you know, the operating line we already discussed in the normal distillation when we have a continuous distillation. And if you remember, we have this equation for this line here. And as you see here, we have at constant L over V, you will have different XDs. Every time you have different XDs here. Okay. Tamam? Okay. So the way how we're going to solve this one or this equation is basically to find the integration from initial concentration of the more volatile component and the residual to the final concentration, okay, because it's unsteady state, and that will actually that will depend on the quantity will be left after the operation. So this one is function of time. Every time we're going to have W and X, W and X. It will depend on how long we continue the operation, and with starting point of W0 and X0. Now, if we want to calculate the time required using a constant boil-up rate, which is the V here, the time will be W0 minus W at any time divided by V multiplied by 1 minus L over V. Now, how did we get this equation, guys? Do you know? Do you have any idea how did we reach this one?
By doing material balance?
Yes, so it's basically by material balance, or if we want to be more precise, I can take you back to this equation, this one, the one that we used in the simple distillation. So you're basically going to see, sorry, I got you back, long way back here, just a moment. The one that we used when we derived the equations for the Yeah, it's not this one. Yeah, this is the equation when we did integral balance. We said W is equal to double zero is equal to W plus dt. So we're using the same equation now, okay? But now there is some kind of a modification. Now here we don't have any reflux, so D is going to be just substituted here. But in our case, here we will just use the same principle or the same integral balance, the same idea, but with a little bit of where we go here. That's it. Yes. Now, if we start with the same equation, W, okay, W0 uh, is equal to W plus TD. Now, you have to remember we have rectification section here, and when we have something going to be returned back. So now D is basically going to be, this is D, this is L, and this is V. Now the constant boil up is the V, and we have a constant reflux ratio. So we would like to have some sort of an equation that will use the constant parameters, lemma H, lemma R, and V. So in this case, if we remove D, it's going to be, what's the value of D here? It's basically going to be V minus L. And if we take V common, that will be L over V. What about R here? Where we get R from? R is basically, if you go back to the definition of V is equal to L plus D. If you divide by D, you're going to have V over D is equal to uh, L over D plus 1. So this is going to be your reflux. And if you substitute with this one, you can easily obtain this relationship. Okay. Now I have this equation in terms of R, the flux ratio, and in terms of L. Sorry, in terms of V. Because I have the constant reflux ratio, okay, and I have constant boil up rate. So now if I want to calculate how much time we need to evaporate, let's say 50% of the initial charge, I will use this one. And of course, I will be given a reflux ratio and the boil up rate value. Now the boil up rate value is in terms of time because it's going to be some kilomole per hour or something like this. Okay. Now, if I want to calculate the average mole fraction, because I have constant reflux here, so as you know, constant reflux, it means this is your equilibrium line, and constant reflux, that means you're going to keep the same slope. In order to do that, what will happen to your XD here? Your XD will start to decrease. So then at some time, after some time, you're going to have some average value. These are XD2, for example. This is probably XD1, and this is XD2. It depends on how many XDs you're going to work. It depends on how long you're going to operate this distillation process. So basically, in order to calculate the average value of the XDs, you will use the also the integral balance, but in this case, you're going to use the component integral balance. A component integral balance will be used to determine the average value, the average mole fraction of the more volatile component in the distillate. Okay, and XW is just the instantaneous concentration of the more volatile component in the residual and the one left behind. Okay, Wt is the quantity at the final time after we stop the operation, how much left in the still pot. And W0 is the initial charge, and Wt is also the quantity or the amount of residual after T time. Okay, guys? So now let's see this example in which we want to evaluate or discuss the constant uh, reflux ratio process. So you have a three-stage batch rectifying section, sorry. So now this is three-stage, number of stages, three stages. Rectifier column, and he is now mentioning that first stage is the still pot. So that means how many stages we have on top of this one? We have two stages plus the reboiler. Is charged with 100 kilomole, so W0 is basically 100 kilomole of 20% benzene, so that's going to be X0 is going to be 0.2. Okay, at constant reflux ratio of L over V is equal to 0.5. So you have L over V here is equal to 0.5. Now from L over V you can calculate R because you know L plus D is equal to V. So now if you have L over V, that means if you divide by V, no, sorry, if you want R, then you're gonna say V over D here is equal to R, this one, 1, L over D plus 1. So now L over D, but in L over B is equal to R over R plus 1. Okay, this is it, R over R plus 1. There's no need to waste time to derive this equation. L over V is equal to R over R1. So if you have L over V, you can get easily R from this equation. Type. Or you can use L over V directly. There's no problem with that. How many moles of charge must be distilled for an average product composition of? Okay, so now the given information is X average. Of course, in the distillate is equal to 0.7. And how many moles of charge must be distilled? So how much we have to continue the operation to remove this. So how much W? Okay. The phase equilibrium curve at column pressure is given in this figure. So it is in this figure you see here. And if the boil-up rate is constant, so V is equal to 10 kilomole per hour. What is the distillate time and what is the operation here? Okay, so you have a batch distillation that contains two stages above the boiler. So we have three stages, in fact. Initial amount of the feed is equal to 100 kilomole, and the composition of normal hexane is equal to 20 mole percent. If the reflux ratio given as this one internal reflux ratio, by the way, is equal to L over V is equal to 0.5. He wants you to calculate how much is W or W minus Wt of a child must be distilled. So how much the final, how much D, how much you have to remove, how much you have to collect from this chart, which is 100 mole. If the average product that I want to produce should have a concentration or mole fraction of 0.7. So this is my criteria. I want to know how much I have to remove or how much I have to distill it to obtain an average concentration of 0.7. He is giving you the phase equilibrium curve, and he is telling you also the boil-up rate is equal to 10 km per hour. So very straightforward, I guess. It is just to start the drawing of this line. A series of operating lines and values of examples are located by trial and error. What do we mean by trial and error? Now, if you remember, okay, uh, the x average, this is the equation that we used. Let me take you back to the equation. Yes. Let me wipe all this one. You see, this x average is given here. And we know x average is function of x and wt. And we don't know xt or wt. So what we mean by trial and error. So we're going to solve, we're going to assume x, okay? From this x we will obtain w. Where we get this equation? We get it from here. Let me wipe here also everything. So we assume x, and we do the table, and we do the integration of this term, and we obtain w. Now I have w and x. I go to this equation. I have w now and x, and I find the average. Now, if the average is exactly the one that he wanted, which is 0.7, then that means my x and w is okay. If not, then I have to do another trial. So this is what we mean by the trial and error. Okay, so we'll have to assume, that's what he's telling you, a series of operating lines and values of x, w are located by trial and error procedure. Now, of course, we start with xw, 0 is equal to 0.2. Okay, now, and you know xw will have to decrease. There's no way xw is going to increase because you are referring to the more volatile component in the mixture. And therefore, you start with some value, 0.2, and then you start to decrease it. Now, if we start with this initial value, this is the xw0, and base it on the operating line slope, which is equal to L over V, which is equal to 0.5. That's what he said, and it is constant because the flux ratio is constant. Okay. Now, and I know how many stages I have. 3 stages. If I count the 3 stages, as you can see, this is stage 1, stage 2, stage 3, then that will be my xd0 at initial. Okay. Now, this is the starting point. I get xd for 0.09. Sorry, we have to start with 0.09 somewhere here maybe. I again do the same thing, but now my line here is going to be having the same reflux ratio or the same slope with, let me wipe this one here. Okay, now here another line, and you see here we have 3 stages. I will have another xd. So when xw is equal to 0.9, my xd is going to 0.6, for example, this one. When it is 0.5, you can get another xw. When it is 0.35, we'll get 0.05 and so on. So I just showed these figures here. When it xw is, you see here 0.09 here, your xd is going 0.78. This is the first point. Okay, and this is the initial one, xt 0.85, and that will correspond to 0.02. And from this, you can draw several lines, okay, with the same constant reflux ratio. Now, once you have these set of points, now again in the exam, you have to have at least 4 points. Now, the 4 points should be between, and XW should be between zero point 0.2 and any number. So the maximum is going to be 0.2. Okay. And then at each point, you calculate 1 over YD minus XW, because this is the integration, how you're going to do the integration. And these are the values based on your numbers here, the data you obtain from the graph. Once you have this one, you can do the integration now from 0.1 to 0.2. Okay. Now, once you do the integration, you can calculate W here on this one. So now W, based on this equation, will be 85, and therefore D, which is the distal, is going to be 100. This is 100, the initial minus 85. Now, if I substitute in the equation just mentioned before, I see that XD average is going to be 0.7. But in the problem, in the statement of the problem, he's telling me that the average should be what? Should be 0.7. So what does that mean? It means the average obtained from the first trial is higher than the desired value, which is 0.7. So we have to start trying with another XW. Try with another final XW, and then if you do this one, you will end up with trial and error. The correct answer was found to be 0.06. And if you, okay, let me just see, there's any questions? Okay. So now, if you repeat the same procedure with different XW, final XW, and you try to choose values between 0.00, sorry, 0.06 and 0.2, we'll find out W is equal to 78 and D will be 22. If you, if you substitute back now in this equation, you will get the time required to be 4.4. So this value is obtained from this equation. Okay. Any question regarding this one? In the tutorial, we will explain how to do it in Excel, in fact. I think. So this is it for the constant reflux. If you have a constant reflux assumption, if we assume we have a constant reflux ratio, that means all what you have to do is basically going to the second scenario is when we have constant XD. So now when we have XD is constant, that means we have to change R is changing. Now, again, I'm talking about the rectification section. That means we have some stages on top of the still pot here. So now here we have this slope to be changing. It's not constant. Okay. Now, in this case, what you have to do is going to generate, again, you're going to solve the integral equation, that one. But in this case, you will have to generate the table that you will use to do the numerical integration by changing their flux ratio. Okay, and therefore, again, you'll have to specify how many stages you have, And according to that, you can start your initial reflux, for example. Okay, and we will see how it is going to be solved. Now here is the mentioning the minimum reflux ratio. Now minimum reflux ratio, as we said before, is simply to draw the line that is going to cross the equilibrium line, and that line will give you the minimum number of state, minimum XW. Okay. Now in this diagram is trying to explain the idea with two stages, including the reboiler. So that means you have 1, 2. Here is the number of stages, but these are the corresponding to the minimum number of stages. Why it is corresponding to the minimum number of stages? Why do you think it is corresponding to the minimum number of stages? Because you remember when we said if you wanted to calculate the minimum number of stages, that means we will assume total reflux, and that means L over V is equal to 1, and therefore the operating line will not be there. Therefore, when I have two stages, I have to count using this line here, not the operating line of this one. And if you count this one, that XW here will correspond to XW minimum. And this is the idea here. And that's what he's trying to tell you here. Now, again, we will see how we're going to be able to calculate the time needed for any operation. And again, we know XW, W are changing with time. Now, they are changing with time, but the way how they change is completely different. It's not similar to what we had before in the simple or in the constant reflux. Here we have changing reflux. So we will start with this equation here. What is this equation, by the way? What is this equation, guys? Where we got this equation from?
Mass balance.
Integral component balance. But there's something here very clear that we have XD. We don't have XD average here. Do you think it is okay? And why not? Why we don't XD average?
And it's the same everywhere.
Thank you very much. So because it is constant now, we are working on an assumption that we will keep XD. So we have XD constant. And if we do component integral balance, we will say the initial content of the component in the still pot finally will be distributed between the distillate and the residual. And the distillate will have a composition of XD, which is XD constant, and the concentration or the mole fraction of the component in the still is XW. Okay, and if we do that, you will come up with this equation. But all what we're trying to do now is trying to find out or try to develop an equation that can describe the change of XW with time. So what I did here, what do you think, where we got this one from? Where this one is coming from, what this equation is coming from?
Differentiating the above equation.
Yeah, so it's basically we're differentiating the equation here to see how the W is changing with time. Since the only one here is not constant in this equation is the XW. That's why we have dW with time is going to be W0 and XD minus XW will be there. So I have only this one. And if we differentiate with time, I have this square here. And that's why. Okay? Is this clear, guys? Okay. So now what I'm trying to do here,
Or
trying to Sorry?
دكتور
Yes.
عندي سؤال، يعني ما أدري إذا أنت يعني تكلمت عن هذا الشيء أو لا، لأن نسيت محاضرة الاثنين ما شفتها عدل. بس هل الأوبريتنج تايم يشمل الهاي الوقت اللي ما بين الباتشز، يعني لما
Yes.
نصلح الأشياء؟
Yes. The operating time is the time required, okay, to reach XW. So you started with, this is your still, this is your feed. You started with 100 mol, okay. You put it in the still pot, okay, and you know the concentration of your more volatile component to be XW0, and you have 2 or 3 stages above the still pot, and you try to start the distillation, and you wanted to monitor XD. So you wanted to keep XD constant. In order to keep XD constant, you will have to change what? Their flux. So you have to adjust their flux to keep the same concentration of the product. Now, you will calculate, or you wanted to know how much time needed to, for example, distill it 20% of the initial feed, or 30%, or 40%, or 50%. How much time is going to be needed if I want to keep the same XD? And in this case, I will see I have XW, of course, the concentration of the still, of the concentration, sorry, of the more volatile components in the still is going to be changing with time. And also the quantity will be changing with time. Both are going to decrease. So the question usually is going to be how much time I need to obtain or to distill, let's say, 50% of the initial feed. Is that okay?
Yes.
So the time is all, because it's an unsteady state. Now what I did here, I tried to relate, because I want to have an equation that is going to be with respect to XW. So what I basically did here, I tried to find out a relationship for this one here. Where I got this one, guys? Do you think where's this one is coming from? Where this is coming from?
Mass balance, I think.
Yes, mass balance. So whatever, this is your still pot here, and these are the stages, for example, and this is your D here. This is the quantity D, moles, and this is of course their flux here. Some are flux and some is going to be distillate here, and this is your W here. Whatever is going to remove or move from W will go to D. So it is basically one is decreasing and one is increasing. So that's why the change in the W will be opposite to the change in D. So that means if W is decreasing, that means it's minus, D is going to increase because it's going to be positive. Now if I divide by dt, I can get this relationship. Now what is D? What is dt by, sorry, dd by dt? What is this? If I take zooming here, okay, and I have this one, condenser, and I have some is going to be refluxed back, and this is my quantity here. This is D. So if I do mass balance here, I say accumulation is equal in minus out. صح? Accumulation is the change of this quantity D with time is equal to N. How much N is going to be this stream? What is this stream? This is V and this is L. So it's going to be V minus L minus out. Minus out, I don't have anything out. So minus 0. So this is dt by d time is equal to V minus L. And now what I did here is just take V as a common factor. So it's going to be 1 minus L over V. Is this clear?
Yes, clear.
So now all what I'm trying to do here is try to find a relationship that I can use to calculate the time here. So what is the relationship is going to be this one. So I'll take this number, I'll put it here. So I have this equation. And as you can see here, I have xd is constant, xw0 is constant, v is also constant because the boil-up rate w0 is constant. And I will collect all other terms in this integration term, and I can get from xw to xw0. And you will see if you do that, you will see there is a minus sign here. That minus sign will be compensated or will be used to change the integral parameters here. Instead of from xw0 to xw, because of the minus sign, it will be from xw to xw0. Okay. Now I have L over V is not going to be constant. The refluxation now is not constant because I'm working on an operation that will maintain XD constant, opposite to the previous one. And now XD is constant, this one is constant, but this one is not constant. So I have XW is not constant and this one is not constant. How I'll be able to solve this integration? Basically, you will have to draw a series of arbitrary operating lines, each with different slope. We will see that in next lecture, inshallah, class, where we explain the two examples more importantly. And then step of n stage, so you know how many stages you have. And each operating line to find it is corresponding xw. So for each LV, you will have xw here. And then you can find this term here. So at different xw's, you will have different values for this term, and then you can do the integration. And that integration, you multiply it by xd minus xw0 over v, and multiplied by w0, you will find out how much time required to reach this xw, because this time is going to be function of how much you want to continue the operation to. For example, to reach xw 0.1 or 0.05 or whatever value. Okay. Any questions?
Dictor,
Yes.
when we are integrating numerically, like which option is the most common? Is it the Simpson's rules, the quadratic, trapezoidal? Which is like the most appropriate?
Well, what I use basically, I'll tell you exactly what I use. So if I go to, I use trapezoidal rule, this one. I show you this one. But it's not necessarily to follow me, by the way. The one that I show you here, where is that? I think, yeah. Sorry, this one. One that I explained it in. Yes, I use this formula, trapezoidal rule. If you want to use any other one, that's fine. But I usually use this one. Okay, so you're basically going to have set of points, and you're going to have this h, which is this step, divided by the number of points. It's up to you how many points you have. Basically, we ask students to have at least 4 points in each example or in each problem to be solved again. Okay.
Yes.
Okay, so we have this example. We finish with this one. Again, you have three-stage batch still boiler and the equivalent of two equilibrium stages. So usually you have two stages plus the boil. But when you're going to solve it, you're going to you count 3 stages. It's loaded with 100 kilomole of liquid containing mixture of the soil. This is XW0, so XW0, and this is W0. And obtain of course, it's a binary system. A liquid distillate of 0.9 mole fraction exchange is to be maintained. So this is your XD to be fixed by continuously adjusting the reflux ratio while maintaining a distillate rate of this one. So this is your boil-up rate. This is your V. What what should the reflux ratio be after 1 hour when the accumulated distillate is 20 kilomole? Now this is your D here, final D is 20 kilomole. Theoretically, when must distillate accumulation be stopped? Assume negligible holdup and constant molar flow. Now these are just to show you or to emphasize the fact that you are working on the same basis or on the same assumption that you use when you work it with the Cape tail method. So now I have W0 and I have X0 and I have XD and I have D here 20 kilomole. So that means W is going to be 80 kilomole because the two should be W because W0 must equal to W plus D. This is the integral or total integral balance. Okay. And from this, I can use this equation. I have XD is equal to this is integral balance. Also, I can do component integral balance. I can calculate XW, the last one. Since I know all of the information, I know how much W left, which is 80, and I know XD constant. I can tell XW is equal to 0.4. So this one is component, similar to the simple distillation. Back to component integral balance. And from this, we can rearrange this equation to obtain XW as a function of XD here. Okay, so this is the first parameter that we want to calculate, and we know XW is equal to what? 0.4. Okay, so now what we will do, we try to do the solution by trial and error to obtain XW 0.4. As you see here, we want to have XW. This is your XW here. If you go there, it's almost 0.4 here. Okay, and which is going to correspond to L over V 0.22. How I measure this one, guys? How I know L over V is equal to 0.22, guys? Who tell me? So what I do, I try to draw arbitrary lines, of course, maybe like this one or like this one. Of course, I start from the XD, and I count the 3 stages, and the one that is going to give me W.4 is going to be my initial reflux. Okay, that will be my initial reflux. Why? Why this is going to be my initial reflux, guys?
ممكن نفس فكرة الفيديو ستيج في chapter 7.
لا، لأن هو احنا حسبنا XW to be what? 0.4.
0.4.
So this one is not the initial reflux. Do you think it is the initial reflux? Do you think it is the initial reflux?
initial reflux مو 0.
Initial reflux, or when we say initial reflux, that should represent XW0. Okay, because XD is going to be the same. So now, in order to say this is the initial reflux, or this is going to represent the initial line, we have to obtain XW to be 0.5 and XD is going to be 0.9, which is not the case as in this line. So what does this line represent? It's representing the reflux in the final stage, or after we obtain this quantity, after we obtain D, because once we have D here, 20, I was able to calculate XW should correspond to 0.4. So now D now is 20 and W now is 80. It's not going to be W0. So now this one is after some time. So it is at the final conditions. Okay. Now from this one, I can get L over V is equal to 0.22. How I get L over V, by the way? Once I know the draw line, once I draw the line and I was able to confirm that flux ratio or that slope of this line will give me XW to be 0.4, I can easily get the slope. I will just extend this one to here, and I can say the slope here, L over V, delta Y over delta X. So I can use this point and this point to obtain delta Y and delta X, and that will be easily calculated to be 0.22. Okay. Now from this L over V, I can obtain reflux ratio and is equal to 0.22 over 1 minus 0.22. Okay. Now, at the highest reflux rate possible, what we mean by at the highest reflux rate possible? What does that mean? It's going to
100% equilibrium.
no, it's equal to it is representing the total reflux. When we have infinite reflux, that means we have to, you see, the stages has to be cutting the diagonal line. And if we're going to assume we're going to have total reflux with this XD, so the maximum or the minimum XW will be 0.06. Because you're going to work under total reflux, which is represented by L over V is equal to 1. Okay. Now the time can easily be determined from the previous equation, and you can get the time to be 2.62 hours to obtain this reflux, or to obtain, and as a matter of fact, to obtain D equals 20. Okay. Is this clear? Yes.
Total reflux. You said it's similar to minimum reflux. So the minimum reflux here is 1?
Now here is the highest reflux rate.
عكس يعني.
When we have this column here, and this is your V here, and this is your reflux here, okay? Now, when we have maximum reflux, that means what? That means we try to, all of this vapor going to be, instead of splitting into product and some reflux, we try to take it back all. And this is maximum flux. That means L almost equal V. And D here almost equals 0. And that was considered to be a close, let's say, to total reflux. When we have total reflux, we will have what? Minimum number of stages. But the same, now we have already the stages. We have 3 stages. So now what we can get out of this one, that means we're going to have this maximum or minimum XW. Okay, so now you have to understand, when we have total reflux, it will represent the minimum number of stages required, and also will represent the batch distillation here, the minimum XW that you can obtain. Any clarification is required? This one I will explain it inshallah next lecture, and on Monday next week inshallah. It's also 100 kilomole mixture of 60-40. Batch distillation at 1 atmospheric. The column has 3 trays, a still pot, and a total condenser. The top product contains the final concentration of residual is 4, the flux is saturated liquid, and V is equal to 10. What is the amount of top and bottom products? What initial and final reflux ratio should be used? So we have constant D, XD, sorry. And what would be the operating time? The average relative volatility of the mixture is. Now he is giving you the equilibrium data in terms of relative volatility. We will go through this example. I think we will have another example regarding the constant reflux ratio as well. And that by that, I think we will finish chapter 13, inshallah. We'll have tutorials. So on Monday, we have problem solving tutorial. We will try to cover as many ideas as possible to in this topic, inshallah. So hopefully you will be able to prepare, revise all the equations that we had. If you have any questions, we can discuss it, inshallah, on Monday, plus the problem, inshallah, solving activities that we will have. Okay, any questions?
دكتور
Yes.
هاي الكالكوليشنز هل يعني نطبقهم على batch distillation columns of different sizes يعني لو كانوا إنه very very small بعد يتطبق عليهم؟
Yes, as long as they have 3 stages or 4 stages, yes.
زين لو عندنا batch distillation columns إنه ويا بعض يشتغلون يعني موصلين ببعض.
كيف batch distillation موصلين ببعض؟ Can you
يعني
explain
ناخذ
this?
الباتش واحد بعدين نروح نحطه في الثاني كذي تخلصه.
يعني قصدك let me just try to explain. And for example, you have batch distillation like this one, and then it's going to be connected to another batch distillation.
Yes.
This one, that means you are working in a series of batch distillation. You have to derive the model equations. You have to find out another equation. Now, the equations that we explained are specific for this type of distillation. If you have, like, for example, batch distillation in series, or they are maybe in parallel, then you have to develop the equations. And you are solving these equations, or you derive these equations based on the configurations you have. Now, the configuration we have is just either simple pot that is going to generate the steam by boiling, and you have a distillate product, or you have simple distillation with some stages above the still pot. And in both cases, you have to differentiate. You have to distinguish between the equations that you're going to use. But if you have a series, one in series, then you probably have to develop the mathematical formula for this separation.
بس بيكون نسوي بالانس حق الأول بروحه الثاني بروحه بعدين total balance كذي.
Yes. Yeah, that could be something. For example, the unsteady state, one multi-stage process. It's multi. It's not going to be easy to develop the equations, but you can consider the. You have everything changing with time. It's not easy unless you wanted to, for example, fix the distillate composition of the first, for example, batch distillation. Therefore, you will be more comfortable with developing the equation for the second batch, and you continue with this one. But if you're going to assume XD is changing with time, so you wanted to fix the flux ratio, so then it's not going to be easy. You need a computer program to solve it, not just a graphical solution. But the question may be more, can we have batch distillation for multi-components? Yes, you can have batch distillation for multi-component as well. But in this case, you will not be able to solve it graphically as we showed now. You will have to use, as I said before, either Polymath or any other software, because you will be dealing with more than one differential equation in this case, because you have more than one component. And each component will be changing with time. So therefore, you're going to have, for example, dx1, dx2 with time, dx2, 3 with time, and so on. It's very similar to what you have in kinetics, if you still remember.
In a reactor design like this.
Yes, because in reactor design, also you have something changing with time, and sometimes you have more than one component. And therefore, you have to represent each component with its own material balance and rate equation.
دكتور يصير تعلمنا في هاي كيف نستعمل الترانزيت كونديشنز، لان احنا ما يعني الكمبيوتر ابلكيشنز كان تركيزنا 100% على
انا خايف اعطيكم من هايسس وبعدين يصير فيها هيدك ويصير فيها العويل، واو الدكتور بيعطينا حاجات ما بناخذها. والله انا to be honest by the way يعني my idea
بس في الريال
separation course يعني separation in general خلاص ما في حد يعمل في الجرافيكال ابروتش يعني. ففي الديزاين في الريديزاين كله بيستخدم هايسس يعني. وحتشوفوا لما تاخذوا كورس اللي هو ان شاء الله 423 plan design project, we're not going to ask students to do any distillation column design using graphical methods. Then it's going to be a waste of time, and it's not going to be an accurate approach. Since you have the tools now ready and available, why should we go back to do some graphical or manual calculations? It's not really wise anymore. But we will try. We'll try to give you there is assessment, inshallah, that you will be asked to do something using HISIS, inshallah. Okay.
تمام، مشكور دكتور.
دكتور يعني هاي كلها approximate يعني solution، بس إنه هايسس بيعطينا ال accurate ولا still approximation؟
HISIS accurate. Accurate compared to the graphical solution, not accurate compared to the real data. Real data will require sometimes some experience, a little bit of experience, but also will depend on the process that you're trying to simulate. In fact, it is sometimes we cannot do it by HISIS, by the way. Sometimes we have to use some experimental data to validate our model first, and then we can investigate the separation. So it is not easy, but by all means, it's going to be more accurate than the graphical solution or the manual, and it's going to be more robust, especially if you are going to compare it with the shortcut methods. Shortcut methods are there also, but we use it usually if we're going to do some optimization for any distillation column. Instead of having a rigorous method, it's because the rigorous method means you're going to have a loss of memory of the computer, especially if you have 10 or 20 components, then it's not going to be easy in terms of computer space. But it is well established now. Most of these HISIS modules are very well established and validated a long time. Any other questions?
دكتور عندي استفسار ثاني شوي ما له يخص بالدرس. الميد ترم بيكون اوبن بوك صح؟
والله اللي في الكامبس يمين؟
ايه اذا ما عندنا
انا احب يمكن حتى لو اوبن يكون اوبن شيت، لان الاوبن بوك حيخليك تحوس في نفسك يعني احيانا يعني that's my idea يعني. احنا ممكن نسال الطالب او we'll ask the students to provide، او ولا احنا نفسنا في ورقه الامتحان we will provide all the equations اللي احنا نعتقد ان هي محتاجينها يعني الطلبه يعني. بحيث تكون more compact العمليه، ما يكون في الا يعني زي ما شايف كوفيد 19 ومش عارف ايش، فكتب وكل واحد حيجيب كتب وحيجيب هذا المراجع اللي شافها في حياته كلها حيجيبها معاه خايف من الامتحان، وهذا حيجيب الامتحانات القديمه كلها معاه، فحيصير ايش لخبطه في القاعه يعني. واحنا هذا we don't want يعني we don't want to say it يعني. بس احنا we will update you by the way, don't worry. هو خلال الاسبوع القادم once we know what exactly the test is going to be يعني that will at least help us to announce what exactly is required in the test يعني what sort of material that you have to bring with you.
تمام، لأن مو مشترية الكتاب فكنت أبغى أعرف هل نحتاجه أو لا، أستعمل الأونلاين فيرجن.
لا، هو ما اعتقد ان تحتاج الكتاب. انا في تصوري حتى ولو حيكون مطلوب منك انك انت تحضر معك ورقه ومكتوب فيها most of the equations اللي you probably need يعني. اوكي.
Okay, thank you, doctor. Have a nice day.
Thanks a lot. Okay,
Thank you.
all the best. Inshallah, have a good weekend. See you inshallah Monday. We'll finish inshallah this batch, this selection. Thank you very much, guys.